Okay, this is the recording for lesson 4.4 from Unit 3, Math 1100. I'm going to be talking about logarithmic functions. All of this is a review from material that you learned in Math 1050. Specifically, these two topics here, expanding logarithmic expressions into multiple logarithmic expressions. That's useful for the next lesson, lesson 4.5, when you're taking a derivative of a logarithm. And then solving equations that involve logarithms, that's going to be helpful to review for lesson 4.6. So like I said, none of this is new material. It's stuff we've seen before. And like lesson 4.3 was specific about the exponential function with the base e, lesson 4.4 is going to be specific about the natural logarithmic function. So when we are expanding a logarithmic expression, what we're going to start with is a single logarithmic expression, a logarithm of a term, and we're going to expand that using these three properties. First one's called the product property. Product meaning multiply. When you're taking the logarithm of an expression that involves a product, a times b, then you can expand that into several logarithms using a plus sign. If there had been a product involving one more factor, like multiplied by c, we would have just added one more logarithm there, like that. Now, the second rule is called the quotient rule. If you're taking the logarithm of a quotient, meaning something dividing, it's got a numerator and a denominator, you can expand that into multiple logarithms. The natural log of the numerator, subtract the natural log of the denominator. It's always the numerator first and then the denominator. And the third rule is called the power rule. Now, if you recall from what you learned about logarithms, a logarithm and base often will cancel out, but only if the logarithm and the base match. So the natural log, if you remember, has a base e, which certainly is not the same as a base a, so these aren't going to cancel. But what you can do is the exponent moves down in front of the logarithm and becomes a coefficient or another factor. So you end up with x multiplied by the natural log of a. So it's a rather short lesson, not too heavy on the homework either. Two main parts, just practicing again what you've already learned and probably practiced last year in Math 1050, but rewriting the expressions. In this case, we're expanding it into several logarithms. And like I mentioned at the beginning, it's going to make things easier once we start to differentiate logarithmic expressions. If we were trying to find the derivative of this expression, that could be pretty tricky. But if we were to separate this into smaller logarithms, it's going to make the derivative much easier to find. So the expression inside the logarithm, this expression inside here is a quotient. It's got a numerator and a denominator. So the first rule we're going to use is the quotient rule right there. So we write this as the natural log of the numerator minus the natural log of the denominator. Now, this first logarithm, natural log of x squared times y, the expression inside here has got a product. So we can follow the first rule here, the product rule, and expand this one into two more logarithms. So it can be written as the natural log of the first factor plus natural log of the second factor minus natural log z cubed. Now, some of the remaining logarithms here have exponents, natural log of x squared, so we can take the exponents using the power rule here, rule number 3, and write those exponents as coefficients. Part B, same thing, just rewrite the logarithm. Now, this isn't a product, nor is it a quotient, so we're not going to use the product or the quotient rule to expand a logarithm. But the cube root can be rewritten as an exponent, so the natural log, instead of the cube root of 4x minus 1, we can write this as 4x minus 1 to the power of 1/3, and now this becomes a power rule, this rule number 3, where we can have this exponent just move down in front of the logarithm. So we can write that as 1/3 times the natural log of 4x minus 1. And really that's it for the practice of expanding logarithms. Now to the second part of the lesson, solving equations. We're going to solve equations that involve logarithms. There's two types we're going to see. This first type involves exponential terms, e to the x minus 1, which we're going to have to use a logarithm for to solve. And the second type of equation actually has a logarithm in the equation, which we're going to have to use an exponential to solve. So for the first type of equation, an equation that involves an exponential expression, we've got to isolate that exponential term. So e to the x minus 1 needs to be all by itself on the left side of the equation. So I'm going to have to add the 3 over. Now, what I'm solving for is x, and x is an exponent. You can't solve for a variable if it's an exponent. So what we need to do is somehow cancel that base. If the base weren't there, then x minus 1 would just be an expression, not an exponent. So hopefully you remember from your 1050 lessons that one of the things a logarithm does is cancel a base, as long as the base of the logarithm matches the base of the exponential. So we can use a logarithm to cancel that base, but it's got to be a log base e. Now log base e is never written like that. It's always written as natural log. Natural log has a base e. And so when we use natural log with an exponential that's got a base e like this, those are inverse operations, so they cancel out. Now this is an equation, so you got to do the same thing on both sides. Now that this base is gone on the left side, the base right here has been canceled with the logarithm, so the x minus 1 is no longer an exponent. You can add 1 to both sides to get x by itself, so x equals the natural log of 10 plus 1. Now the other type of equation that you'll see in the homework is one that already has a natural log in the equation. So it starts very similar. In order to get x by itself, we have to eventually cancel that natural log. Now in order to do that, we have to get the natural log expression, the term that involves a natural log, isolated. We need to get by itself. So this term right here needs to be the only term on that side of the equation. So you got to subtract the 6. Now 3 is multiplying the logarithm there, so the opposite of multiplying, we can divide by it. So we have the natural log of x equals 2/3. Now x is inside a logarithm, so we need to cancel that logarithm in order to get x by itself. So if you recall from the previous example, the natural log and base e are inverse operations. So if we already have a natural log, we need to use a base e to cancel it. Now, mistakenly, a lot of students will just put the e right here. Well, that's multiplying. That's not acting as a base. E has to act as a base with the natural log as the exponent. So what I have is the base e, and the natural log of x is the exponent. So I've got to do the same thing on the right side. E is the base, and 2/3 is the exponent. Now a base e and a natural log are inverse operations. They cancel each other out. So now x is all by itself. We have x equals e to the 2/3. Now what's never a bad idea, especially with these types of equations, is to check answers. So if we go back to the original equation and check our answer, we've got 6 plus 3 times the natural log, and now we can input our answer, e to the 2/3, and that's supposed to equal 8. Well, here the natural log, e cancel out, so we've got 6 plus 3 times 2/3, and that's supposed to equal 8. 3's cancel, so we've got 6 plus 2, so looks like that one checks out. If we come back up here, we've got e, and instead of x minus 1, we've got natural log of 10 plus 1. So this is where the x was, and then we've got the minus 1 because we're supposed to have x minus 1. And then we have a minus 3, and that's supposed to equal 7. Well, the minus 1 and a plus 1 are going to cancel. And remember, if we have a base e and an exponent of natural log, those are inverse operations. So the only thing left there is the 10. So we've got 10 minus 3, which equals 7.